Hi, I'm Matteo Risiglione, and today I will be presenting a passivity-based control for haptic teleoperation of a legged manipulator in presence of time delays. The work was carried out at the Robotic System Lab at ETH Zurich in collaboration with the iBotics Lab at the University of Twente. Let's now dive into the details of the work. Haptic feedback has been shown to be of paramount importance in teleoperation. However, when teleoperation is performed over the network, it's challenging to have good transparency and maintain stability. Different are the elements that can threat stability, like delays and packet losses and control settings. And instabilities are manifested as oscillations, as it's possible to see in these two videos, and it requires additional damping from the operator or from the control unit. Related works of haptic teleoperation for legged robots had been more focused on the balancing problem of the teleoperated robot by bounding the operator commands or by providing to the human operator an haptic feedback that can inform him about a possible loss of balance of the teleoperated robot. However, in all of these works, delay have not been taken into account. Therefore, the motivation for our work was to take into account delays and to create a control framework that is robust to it and to other destabilizing elements. We apply this approach to our quadrupedal mobile manipulator. The main idea was to exploit passivity theory to achieve stability of the system. Passivity theory is a tool that allows to reason with energy and does not require to model all the elements present in the loop, like the human and environment. The proposed passive control architecture for haptic teleoperation in literature, they all try to dissipate the desired control law to preserve passivity. However, this dissipation layer can break the feasibility of the control law. Being the wall body controller for our quadrupedal mobile manipulator, obtained by solving an optimization problem, we didn't want to break the feasibility of the control law itself by adding a dissipation term. Therefore, we propose a controller which optimizes over transparency while respecting the energy bounds to preserve passivity. I'm going to provide some background on passivity theory. If we consider a generic system sigma where U denotes the input and Y denotes the output, this system is said to be passive if there exists a function called storage function, which rate is bounded by the product input-output. If we think the product input-output to be the power injected to the system and the storage function to be the energy of the system, then this inequality is telling us that the rate of energy of the system cannot grow more than the power injected. This is why the system is called passive. If we consider two passive systems, let denote them sigma 1 and sigma 2, and we interconnect with the following power-preserving feedback interconnection, where we have a condition on the feedback interconnection itself, then the combined system just satisfies the following two properties. The total storage function is given by the sum of the individual storage function, and the rate of the total storage function is equal to 0, which means that the combined system is passive. We have just seen that interconnection of passive systems is passive if every component is passive, and if a power-preserving interconnection is established between the components. If we take now the control loop for our application, starting from the left, we have the master device, the bilateral teleoperator composed by the control unit and the communication channel, and the slave robot. Being master and slave mechanical system, they are passive. Therefore, the only two requirements that need to be imposed are the passivity of the bilateral teleoperator, which can be compromised by delays and other elements. And we need to establish a power-preserving interconnection between the bilateral teleoperator and the two teleoperated robots. We don't want to create energy while exchanging it. The first requirement will be achieved thanks to the idea of energy tanks, which are now gonna define. Energy tanks are lossless dynamical systems which are used to store energy exchange between robots and controller. And the energy in each tank is given by the sum of two components, the energy exchange with the world plus the energy exchange with other tanks. Indeed, if we see the equation describing the evolution of the tank, we can see that the rate of the state associated to the tank, denoted here with x, is given by the contribution of the control effort plus the power exchange between the tanks. We interconnect the master and the slave tank to the master and the slave robot respectively as follows, with this power preserving interconnection, where the elements WVM and WVS are still values computed by the controllers. The structure DM and DS are defined as the one in the definition of the power preserving feedback interconnection given in some slide before. We can see in the following diagram how the two tanks are interconnected to the two robots, and the structure DM and DS regulate the flow of energy from the tank to the robots based on the amount of energy left in the tank. Thanks to this interconnection, the rate of energy in the bilateral teleoperator matches the power flowing from robots, so the bilateral teleoperator has been made passive. However, the energy level inside the tank has to be positive to avoid loss of passivity for the tank, and this can happen in discrete time. So we'll see how to compute the control action to consume no more than energy left in the tank. There are two teleoperation modes that have been created. One is the end-effector position control mode, where the position of the master device is mapped to the position of the end-effector of the teleoperated robot. And then there is another mode which is used to navigate around. And in this mode, the position of the master device is used to control the velocity of the base of the teleoperated robot. However, the signals of the master are not directly sent to the wall body controller, but there is a layer in between, the wall body planner, which maps the user commands to references for robot's base and limbs. It has to deal with the coordination of the base and the limbs, as well as with the gate generation. And the wall body controller solves a hierarchical QP to determine the vector of desired acceleration and desired contact forces, denoted in the equation with the letter XC, and those are mapped with inverse dynamics to the torques, USC. The vector of generated torques satisfied thanks to the formulation of the QP, friction cone constraints, actuation limits, and contact constraints. While being in end-effector position control, at the master side, we first derive an update for the energy tank. Since the controller is implemented on an embedded unit, a discrete-time rule needs to be computed to update energy tank level. And we can see that based on the energy left in the tank, we modulate the haptic feedback. When energy is not present or is beyond a certain threshold that we define to avoid the singularity in the tank, we add dissipative term to extract energy from the master. While at the slave side, we first find an update equation for the energy left in the tank, and we impose that the energy that can be consumed by the control input is limited by the amount left in the tank minus a certain threshold. We reformulate this inequality as in the QP notation, and we had other two equality and inequality, one for the motion of the arm and another one to preserve the motion direction. We don't want the passivity acts on the desired motion direction. While being in the base velocity control mode, due to the limited workspace, the master position is sent to a velocity-like signal that we call RM. The master is made passive with respect to the input-output port UMC RM, where RM is defined as the sum of the current velocity of the master plus a scale position. A local control action needs to be added in the form of a spring and a damping term to the control input to make it passive with respect to the output RM. And the same modulation for WVM occurs as the one defined for the end-effector position control mode. For the slave controller, we first define an update for the energy tank as we did in the end-effector position control, and this time we have to penalize the ground reaction forces being the base unactuated system. We rewrite the passivity constraint for the base in the QP notation, and we add inequality to preserve the desired base motion direction. Here is a summary of the task in the wall body controller. We enforce the motion direction task at a higher priority than the passivity and the tracking. Having the passivity and the tracking at the same priority allow to respect the stability requirements while still guaranteeing a good tracking performance and avoiding overly conservative behavior. To validate the approach, we perform different experiments. In the first experiment, the human operator moves the haptic device along a predefined trajectory. The haptic feedback is generated by the displacement error between the master and the slave measured position. And we can see that on the left side, in the case without passivity layer, the two devices show an oscillatory behavior. While when passivity layer is implemented, it leads to a smoother master and slave trajectory. As we can also see from the plot of the energy tanks, in the case without passivity layer, around 6 seconds, when the two systems start to really diverge with respect to each other, the energy tank of master and slave goes to a negative value. And this is in the second experiment. We perform an haptic interaction. We use the same feedback as before, and the hands of the slave robot was shaken by a human operator. We had to tune the gains of the haptic feedback higher to allow the operator to perceive low forces, and this can lead to more aggressive behavior, as we can see in the case without passivity layer. While when passivity layer are implemented, this leads to a more conservative haptic feedback. In the last experiment, we controlled the base velocity of the slave, and we implemented the haptic feedback based on the velocity tracking error at the slave side. This type of haptic feedback allows to realistically perceive external forces and to capture their effect without the need for any haptic sensory feedback. We can see in the case without passivity layer that the master device goes unstable with the delay introduced, while in the case with passivity layer, the human operator is able to fulfill its task. We also noted from the experiment that with passivity layer, the velocity tracking error is sacrificed. This is the price to pay for passivity, since we penalize for the ground reaction forces in the wall body controller formulation. In the last experiment, we control the base velocity of the slave. We use haptic feedback based on the velocity tracking error at the slave side. We realized that this haptic feedback is able to allow the operator to perceive forces without the need of any haptic sensory feedback. And we have seen that without passivity layer, the master device goes unstable, while when we introduce the passivity layer, the human operator is able to perform its teleoperation task. We realized from experiment that with passivity layer, the velocity tracking error is worse. This happens because we are penalizing the ground reaction forces in the wall body controller to preserve passivity. However, this is the price to pay for being able to perform haptic teleoperation in a stable way when delay are present. We got to the conclusion. We presented a passivity-based approach for haptic teleoperation of a quadrupedal mobile manipulator. We validated the approach in presence of time delays for different teleoperation tasks. And in the future, we could implement a direct force reflection approach where we feedback the force measure at the end-effector with a force sensor, and we can extend the approach to perform more telemanipulation tasks like opening doors or turning valves.
Thank you for the attention.